Hello, I'm Chris Budd and I'm the Gresham Professor of Geometry, and in this talk I'm going to tell you about equations that have changed the world. Now, equations are very important in mathematics and in many other areas of life. I've put up here my favourite equation of all time, e to the I pi equals -1. Why are equations so important? Well, firstly, they are true. They are eternally true. If you want to create something immortal, create an equation. Secondly, an equation compresses a huge amount of information into one formula. What that means is that you can kind of think of an equation as highly condensed information, and by solving the equation, you learn lots and lots about many things. Thirdly, one equation can have many different applications. So the equation e to the I pi equals -1 has countless applications in wave mechanics, in geometry, in physics, and many other areas. And what I'll try to imply and show in this talk is that equations lead to algorithms, and algorithms lead to technology. So let's have a look at some famous equations. Perhaps the most famous equation of all is Pythagoras' equation, a squared plus b squared equals c squared, about the lengths of the sides of a right-angled triangle. And that equation has been around for at least 3,000 years and is just as important now as it was when it was originally invented. Related to that is a to the n plus b to the n is c to the n, and the question of whether that has solutions in integers puzzled mathematicians for many hundreds of years and only recently was solved. And then I have put down two equations due to Leonhard Euler. These are marvellous ones. F plus v equals e plus 2 is the equation for the vertices, faces, and edges in the polyhedron. And then e to the I theta is cos theta with I sine theta is a fantastic equation showing how angles are related to the exponential function. Now we move on to some famous equations in physics. Well, the top one is Newton's equation of gravity, which allowed us to understand how the solar system worked for the first time properly. Schrödinger's equation, which is the fundamental equation of quantum theory. The two famous equations of Einstein, E equals mc squared, showing how mass and energy are related. And the second one is called the Einstein field equations, which modestly is the equation for the entire universe. And I'd like to put Maxwell's equations on. I ran out of space, but they are the equations of electromagnetism, and very important as well. So those are all great equations. Lots of people have written lots of books about them, and you can see those in the transcript. But I'm going to concentrate on my own 5 favourite equations in this talk. And the reason I selected these equations is partly because they have universal importance. You can apply them to just about anything. And secondly, most of the equations of physics or engineering reduce down to these equations when you put them on a computer. And my job, my kind of professional job, is solving problems on a computer. And so I end up solving the same things over and over again, coming from many different applications. And this is why I've chosen these 5. So the first one I call the linear equation. Then the second is the matrix eigenvalue equation. Then we have the Fourier transform. Then we have the Navier-Stokes equation, which is very closely related to physics. And finally, we have what I call the shower equation, which is actually closely related to the problems that we're facing at the moment in the COVID epidemic. So that's what we're going to do. We're going to look at each of these in turn and learn something about them all. The first equation that we're going to have a detailed look at is the linear equation, ax equals b. In this equation, b is something that we know and x is something that we don't know. I would say it's fair to say that the majority of the world's computing effort goes into solving this equation in many different applications. We're going to have a look at an example to do with shopping, but it also comes up in medical imaging, it comes up in weather forecasting, it comes up in finding the deformation of a bridge, it comes up in working out where to put aeroplanes in the world. It comes up everywhere in applications. So let's have a think about what's going on in this. As I said, B is a vector of known values. This can be quite a large vector of known things. X is a vector of unknown things. And A is an operation which links X to B. What do I mean by linear? Well, what I mean by that is if I double B, then the solution is just twice X. And if I have two solutions, I can add them together. And most of the world's problems end up looking like that in some way. What sort of operators do we have? Well, the computational operator we always work with is a matrix. But from physics, you often get operators which are differential operators, such as ordinary or partial differential operators. But when you put those on a computer, they end up also being a matrix. So the question we're always going to solve is, how can we find X if we know B and A is some sort of matrix? Let's think of an example. We're going to go shopping, and we're going to go shopping for apples and bananas. We buy X apples and we buy Y bananas. And in our shop, the apples cost £2 each and the bananas cost £3 each. And we have a total budget of £17. The reason we're going shopping is that we want to make up our vitamins. So each apple has 4 units of vitamin C and each banana has 3 units, and the total vitamin content that we need to get is 25 units. So the question is, how many X apples do we buy? How many Y bananas do we buy so that we make up a budget of £17 and have a vitamin content of 25 units? So what we know is the budget and the vitamin content, and what we don't know is how many bananas and apples that we need. Well, we can write this as a linear matrix equation. The matrix A expresses the link from the number of apples and bananas to the what we have to make up in terms of our budget and our vitamin content. So the budget and vitamin content is the vector 17, 25, and our matrix A is the link between X, Y and that, and X and Y make up the vector X of unknowns. And maybe you can try and work this out yourself before I reveal it. So there's our equation, A times X equals B, as a matrix equation. Well, how do we solve this? Well, we solve it by finding the inverse matrix A, the matrix which when multiplied by A gives what's called the identity operator. And then the equation can be solved by saying X is A inverse times B. Now the problem we're having at the moment has two unknowns, and A is what's called a 2 by 2 matrix. And there is an algorithm for working out the inverse, and you can basically write it down. And there is the inverse written down. And if you apply that to the problem with B is 25 and the vector is 17, 25, you find that the number of apples that you need is 4 and the number of bananas that you need is 3. And you might want to just go off and check that yourself. So that's a fairly easy problem to solve because we've only got two unknowns. But in general, our vectors are much bigger. They are of size n. We say that there are n unknowns. And this problem gets much and much harder to solve as n increases, and that is why it takes up so much computer power. As a rough estimate, the amount of time it takes to solve this problem goes like the cube of n for a general problem. And this really, really matters because, as I said, the equation AX equals B has a vast number of applications in medical imaging, weather forecasting, banking, aircraft, bridges, retail, ... and everyone needs to solve it. And the value of n can be very large. So for many problems, n can be 1 billion or more. 1 billion or more. We have to solve 1 billion different equations. Let me show you a very nice example of where this matters, and that is in medical imaging. So one way to do medical imaging is to shine X-rays through your body and detect the X-rays as they pass through the body. So you shine a large number of X-rays through the body and you see how much each X-ray gets attenuated. And we can then use the information from the attenuation of the X-ray to see what's going on inside the body. But to do that, we have to pose it in terms of the equation A times X equals B. Well, what is X? Well, you divide the body up into lots of small squares, and then X is the vector of the unknown density of the body at each point at each square. And X can be huge. X could easily be 1 million or more unknowns as you try to understand what's going on inside the body. The values of B are the attenuation of each X-ray as it goes through the body. And the link between the two is what's called the tomography matrix, which is something that you can calculate in advance. And if you want to learn a bit more about that, I gave a lecture a couple of years ago called How Maths Can Save Your Life, which goes into this in a bit more detail. Now, in general, the number of unknowns that we have to look at is rather more the number of X-rays that we can shine through, and that means that we have to augment the equation with a little bit of extra information. We call this a priori information to be able to solve it. But if you can solve it, the rewards are immense. And what I'm showing in this slide here are some pictures of the body taken using this technology to show the interior detail. And before this method was applied, the method of shining X-rays but formulating the problem as a linear equation, these pictures were impossible. And medical imaging only became realistic in the 1960s and 1970s because we could find fast ways of solving the equation AX equals B related to medical imaging. And the same reason means that we can do weather forecasting, which you couldn't before, because we can solve this equation. So how do we solve it? Well, there are many ways to solve it. There is a thing called the direct method, which was attributed originally to Gauss, but we now realize was solved by the Chinese in around about 150 AD, and which is kind of to construct the inverse of the matrix and then apply it, rather like I showed you. And that's the method which takes n cubed time if you have n unknowns. A rather better method if your problem is very, very large is to sort of guess the solution and then successfully improve it. And the method of choice at the moment is called the Conjugate Gradient Method, and that's the method that's being used to solve most of the world's problems, including the problems, very much including the problems of medical imaging. Weather forecasting also uses conjugate gradient, but now we're starting to use new methods called multi-grid methods, which seem to be faster than any of the other methods on this slide. And I predict that there's going to be a huge improvement in the accuracy of weather forecasting, simply because we can solve the equation AX equals B better. So that's the equation AX equals B. Pretty well everything in maths and science and engineering ultimately ends up being that equation, and it's very, very important that we can solve it quickly, and that's why it made it as first of the equations on my list. Our next equation is the matrix eigenvalue equation. AX equals lambda x. Here A is a matrix, X is called an eigenvector, and lambda is called an eigenvalue. This equation looks quite similar to the previous linear equation, but now X appears on both sides of the equation, and we have this additional lambda. And what's happening here is we're trying to find a vector which, when multiplied by the matrix A, simply gets multiplied by the value lambda. This equation is incredibly important for problems involving waves, involving sound. It comes up in Wi-Fi, and recently it's found a massive application in Google, and perhaps because of that it's one of the equations that we interact with most commonly in our lives. But before I get onto Google, let's look at a rather nice example which involves singing in the shower. So this is an experiment you can all do. So next time you have a shower, go into the shower and start to sing. And what you do is start with, say, a low note and increase your voice up to a high note. So you go ooh, something like that. And when you do that, you'll find that some notes sound really loud. They're what we call resonant notes, and others are very, very quiet. And the resonant notes are really important if you're designing anything to do with acoustics, because they're the sounds which are going to sound the loudest, and that might be very important, for example, in the design of a musical instrument. So the equation underneath the man singing in the shower is called the Helmholtz equation, and this is the equation for the sound vibrations in the shower. The operator on the left is called the Laplacian, and on the right we have omega squared x, and omega squared, well, omega is called the vibrational frequency. So the solutions of this equation, the values of omega and x, tell us the notes that are going to sound good, that's the omega, and x tells us how the shower is going to vibrate. So in order to find the resonant notes in the shower, we need to solve this equation. Well, this equation, if you put it on a computer and you discretize the Laplacian operator, becomes exactly the eigenvalue equation I put up earlier. So although this is a famous equation in physics called the Helmholtz equation, as soon as it goes onto a computer, it becomes the matrix eigenvalue equation. And if you find the eigenvalues and take the square roots, that gives you the vibrational frequencies, and the eigenvectors give you the vibrational modes. So this is an equation we solve a lot when we're trying to find resonant acoustic responses of structures and many other things. On the next slide, you can see two examples of this in action. On the top, we have Faraday waves, which are vibrational waves in a dish, vibrational water waves, and the patterns that we see there are the eigenvectors, the x's of the equation. The second example is one I really like, is in a football stadium. The spectators, the supporters of the football team often have songs that they like to sing, which are the songs for their football team, and as they sing the songs, they sway to and fro, and they move their arms up and down, and they bash their feet and so on. And it's really dangerous for the stadium if those frequencies in the song and the motion like that is equal to one of the resonant frequencies of the stadium, because if it is, then the stadium will shake to bits. So when they design football stadia, they often look for the resonant frequencies by solving the Helmholtz equation and therefore the eigenvalue equation to make sure that the football stadium is safe. For exactly the same reason, when people go over a suspension bridge or soldiers, they're told not to march in case the frequency of their marching is the same as a resonant frequency, in which case the bridge will shake to bits. So these are very important things to avoid, and you work out what they are by solving the matrix eigenvalue equation. So let's have a look at an example with a 2 by 2 matrix. So if we take the matrix A is 2.5, 0.5, 0.5, 2.5, then if you do the calculation, A multiplied by the vector 1, 1 gives you 3 times of that, and A times the vector 1 minus 1 gives you twice that. So the vectors 1, 1 and 1 minus 1 are the eigenvectors of this matrix, and the eigenvalues are given by lambda equals 2 or lambda equals 3. This is a 2 by 2 matrix, and it has 2 eigenvalues, and that is because it's a 2 by 2 matrix. If you have an n by n matrix, a much larger matrix, then there are, in general, n different solutions to this problem. If you're taking a matrix corresponding to, say, a suspension bridge, then n can be very, very large. It could easily be in the millions, and so there are a million solutions to this problem. At a technical level, we can work these out by finding the determinant of A minus lambda times the identity and solving this for lambda. If you take A to be the general 2 by 2 matrix A, B, C, and D, then the determinant equation gives you a quadratic equation. Quadratic equations have 2 solutions, and that's why there are 2 eigenvalues of a 2 by 2 matrix. It also shows us why quadratic equations are really important. If you have an n by n system, then you end up with a polynomial which has degree n, and that has n solutions. And this is kind of what you have to solve if you want to find the eigenvalues. And solving that's pretty tough. It's not easy to find eigenvalues at all. A lot of effort has to be put into finding eigenvalues, but the effort is extremely well worth it because of the enormous impact this equation has. Let's have a look at some examples. So if you're in engineering, as I said, you want to work out the eigenvalues of a structure to find the frequencies at which it vibrates. If you're in chemistry, you can do the same. You can take molecules and formulate the relationship between those molecules in terms of these various matrix operators. And by doing that, you can actually work out the frequency of vibration of the molecules. And that tells you an enormous amount of the system. It tells you the spectrum of the system, and that tells you a lot about how chemical reactions will work. And similar reasons, similar vibrations arise all the time in physics. Linked to vibrations are waves, and waves are important in acoustics. Maxwell showed that they're important in electromagnetic theory. They arise in Wi-Fi. And to find waves, you end up solving the equation we spoke about earlier, the Helmholtz equation, and that's exactly the matrix eigenvalue equation. And if you want to go into quantum theory, then the Schrödinger's equation, which is one of the great equations of physics we use to introduce this talk with, you need to find the wave functions of that, and the wave functions of the Schrödinger's equation are precisely eigenvectors of the discretized version of this, and the eigenvalues are then very important as part of that. So the matrix eigenvalue problem, really important in engineering, really important in chemistry, really important in physics. But one of the most recent applications, and a really wonderful application, has been realizing it's very important in searching the internet. And I want to tell you very briefly about the page rank algorithm, which was invented by Brin and Page, who are illustrated here, who were the two people that founded Google. And the legend has it that they got the idea for the PageRank algorithm because they were attending a course on linear algebra and matrices and eigenvalues and eigenvectors at Stanford University. So the idea behind the PageRank algorithm is to find a way of ranking the web pages which refer to something. So let's suppose we have Gresham College, then there will be pages which refer to Gresham College, and Google wants to find the best page which contains the most important information. And the way it does that is it assigns each web page a rank. So if the ith web page referring to Gresham College, if there's an ith web page, we give that a rank Ri, and the page with the highest rank is the one that Google will select. So let's suppose that we have a page referring to Gresham. Well, there'll be lots of pages that point to that. For example, my own web page refers to the Gresham page because I'm Gresham Professor of Geometry. So there'll be m other pages that point to that. Each of those pages will have a rank itself. We'll call that rank ij. And each page points to lots of other pages. So I point to many, many pages from my website. And the importance of a website is reflected by how many pages point to it and how important they are. And the formula for calculating the rank of a matrix is to say that the rank of a web page, is the rank of the ith web page is given by the sum of the ranks of all the pages that point to it divided by the number of pages they point to, multiplied by what's called the damping factor, which is generally taken to be 0.85, plus a term which is 1 minus damping factor divided by the total number of web pages. And that's meant to be the chance that you might land on the Gresham page purely by random by pressing buttons and so on. So that is the equation for the rank. And you'll notice it's quite a tricky equation because the rank for a web page is on the left-hand side, but it is also on the right-hand side of the same equation. So to find the rank, we need to solve quite a lot of things. So to give you an example, I take a picture which comes from the Wikipedia entry on PageRank, where we have pages A, B, C, D, E, F, and a lot of kind of small pages. So page B points to page C only, page C points to page B only, page A is only pointed to by page D, page D points to B, and lots of pages point to B, lots of pages point to E, and so on. And if you take that equation for the rank and solve it, for D is 0.85, then the rank that you get for each page is the number underneath the letter identifying the page. So the rank of A is 3.3, for B it's 38.4, for C is 34.3, and so on and so on. And the highest rank in this case is for B, and therefore that is what Google presents to the person that asks about Gresham College as the top hit for Gresham. Okay, and that's the Google PageRank algorithm, and companies are very, very keen to make sure that they get high up in the rankings. But you only get high up in the rankings if your web page is pointed to by other highly ranked web pages. Okay, well, Google has to find what the ranks are, and that means it needs to solve the equation that we put up. And the problem is that that's very big. There are well over 1 billion web pages around, so this is a huge, huge system. But also Google needs to solve it very quickly. So Google search should only last, under a second really. And the way Google works is that it poses this equation as a matrix eigenvalue equation, where the matrix M is called the augmented adjacency matrix. It's how web pages connect to each other. And this is this vast matrix. It's, 1 billion by 1 billion matrix. But we don't need to find all the eigenvalues. In fact, we only need to find the eigenvector corresponding to the eigenvalue of 1. The equation, the PageRank equation, ends up being this simple equation. And there's a very straightforward way to do that. You kind of guess what the ranking should be, and then you iteratively refine your guess by multiplying it by the matrix M loads and loads of times. And if you do that, then this quite rapidly converges to the rank, and that is the rank that then Google calculates. And this algorithm works really fast, and Google makes it work very, very, very fast. And there's a few other things that it does as well to prevent cheating, but that's the basis of it. So Google works by finding the eigenvector of the eigenvalue equation with an eigenvalue 1. And I bet that everybody that's watching this lecture at the moment has used Google many times today already. So you have been solving the matrix eigenvalue equation through Google many times today. So that shows you how important that equation is. My next equation is the Fourier transform. And this equation comes as a pair. It takes a function f, and by integrating it between minus infinity and infinity times a complex exponential, produces the Fourier transform f hat of omega. Conversely, if we take f hat of omega and integrate it using a very similar transform, we end up back to the original function. So the Fourier transform takes a function f to a function f hat, and the inverse Fourier transform takes us from f hat back to f again. Now, why is this important? It's important because the Fourier transform decomposes a function into waves. All functions can be shown to be a mixture of waves, and the Fourier transform shows us how it can be done. Let's give an example where this is kind of important. Suppose we are listening to an orchestra playing. We hear a musical sound from the whole orchestra, and we can record that over a period of time to listen to a concert. But that doesn't tell us what the individual instruments are in the orchestra. The Fourier transform can do that for us. If we look actually at an individual instrument, say a flute, an oboe, or a violin, they all sound different even if they're playing the same note. Why do they sound different? The reason is that as well as the note that they play, they also play harmonics. That's notes of higher frequencies which are a multiple of the original. If we look at the different harmonics, the top picture here shows the flute, which has a single note and the harmonics tail off very quickly, which is why it has a very pure tone. An oboe has harmonics which tail off slower, so it has a sort of richer tone, and a violin which has harmonics which tail off very slowly indeed, and so it has a very rich tone indeed. And this is why the flute, the oboe and the violin all sound very different. Now how can we work out what these harmonics are? Well, very easily. What we do is we take the sound from a flute or from an oboe or from a violin. That's our function f. We then apply the Fourier transform to it, and the Fourier transform produces exactly the graphs that we've got above, showing what the harmonics are. So the Fourier transform shows us what the harmonics are, and you can do the opposite. If we want to reproduce a violin sound, we get the harmonics to be in the right proportion, Fourier transform back, and you get a sound which sounds just like a violin. So the Fourier transform takes one function and maps it to another, and what we've just seen in that example is what happens if you take a sinusoid function and that maps it to a single frequency. If you take a different function, so that the next one is what we call the top hat function, then the top hat function, which is a function which is 0 and then 1 and then 0, it's what you'd get if you go into a room, turn on the light and then turn it off again. That maps to what's called a sinc function, which is a sine wave divided by x. And that gives a kind of decaying out sine wave. The Gaussian function, which occurs in statistics all the time, has the property that its Fourier transform is the same as itself. The Gaussian is actually an eigen vector of the Fourier transform, just like we met in the earlier example. And the final function, what's called the Fourier induction delay function, which comes up a lot in quantum theory, has a Fourier transform which is a Lorentzian, which is 1 over 1 plus x squared. So we have this natural map between one function on the left and the Fourier transform on the right, and we can go back the other way. Have a look at the top hat. The Fourier transform of that is this sinc function, this oscillating but decaying function. And if you shine light through a slit and look at the diffraction pattern of the light on some obstacle a little bit further away, what you get is exactly the same function. The sinc function is the diffraction pattern of light, and you can show that light diffracts according to the Fourier transform of the shape that it diffracts through. So the Fourier transform is an essential tool for understanding diffraction and optics. For similar reasons, it's an essential tool in the telecommunications industry, in image processing, in medical imaging. Chemists use it for spectral analysis, and it is used a lot in acoustics as well. It's the tool which takes us from what we call the time domain, into the frequency domain and back again, so we can see how functions are made up of waves. But it has another use as well. If I send a signal through a channel, so let's suppose we have Alice trying to communicate with Bob through a channel, Alice might make some sort of signal, f of t, some sort of noise, that goes through a channel, and by the time it gets to Bob, that noise will get distorted. That might be some sort of fuzziness that gets introduced as the signal is transmitted. Similarly, we might take a photograph, and the photograph gets blurred as it goes from the original to the image. And there's a mathematical way of working out what this blurring is, how the blurring works, is what's called convolution. And you can show that Bob receives a signal h of t, which is the integral of the function f of t, what Alice sends, multiply by g, which is called the transfer function of the channel between minus infinity and infinity. And that is convolution. And it's a kind of scary thing. It's really hard and takes a long time to work out if you do it using that formula. And what we'll have to do often, Bob gets the signal h of t, he wants to know what signal Alice sent, he needs to find f if he receives h. How do you do that? well, how do you unblur a photograph? Well, there's a beautiful way of doing it. Mathematically, we call convolution h f star g. But if you take the Fourier transform, possibly my favourite theorem in the whole of applied maths is the convolution theorem, which says the Fourier transform of h is the Fourier transform of f times the Fourier transform of g. So if I want to find h, what I do is I take f and g, take their Fourier transforms, multiply them, and then take the inverse, that finds h. But even better, if I know what h is, I can calculate h hat. I know what g is, I can work out g hat. And if I divide h hat by g hat, I get f hat. If I take the inverse of that, that's the original message that Alice sent. So what we see in this picture is a way of de-blurring an image. Here's an example. On the left, we have a blurred image, which would be the function h, which Bob would receive. Take its Fourier transform, divide by the Fourier transform of the blurring function, and then invert, and you get, on the right, the unblurred picture. And this is how de-blurring techniques work when you have a camera or on a computer. And we can use these techniques to unblur photographs. Somewhat similar techniques are used in MRI imaging, and the Fourier transform is an essential component of medical imaging using an MRI scanner. So the Fourier transform is really important. It's used heavily in the telecommunication industry. It is the bedrock of that industry. And one of the reasons for this was that in 1965, Cooley and Tukey came up with an extremely clever way of working out the Fourier transform called the FFT, the fast Fourier transform, which is a computer algorithm which evaluates the Fourier transform extremely quickly. And that computer algorithm, which was implemented in 1965, which had been known about before, but the first implementations were in 65, led directly to the whole telecommunications industry that we now enjoy and the digital technology that is so important in our lives. So the FFT allowed the Fourier transform to be implemented, and that led to technology. I don't know whether it's coincidence, but in 1965, the Beatles brought out the single "We Can Work It Out" just after the FFT had been published. I like to think that it was done in celebration of that great event in mathematics and engineering. My next equation is a system of two equations called the Navier-Stokes equations. These equations look much more complicated than the first three equations, and indeed they are. These are equations which describe the very complicated behaviour of fluid motion. In this system, U is the velocity of the fluid, P is the pressure of the fluid, rho is the density of the fluid, and F is the rotational motion of the fluid on a rotating body such as the Earth. The Navier-Stokes equations were derived by two mathematicians, the French mathematician Navier and the Irish mathematician Stokes, in the 19th century. They were developed from earlier equations called the Euler equations, developed by Leonhard Euler in the 18th century, and that in turn built on the original equations for Newton for his equations of motion. The first equation shows how the momentum of the fluid changes under the action of various forces, and the second equation shows how its density changes. These equations are extremely important in our lives because they are the equations for the weather. Let's have a look at a synoptic chart. This is a typical weather forecast made by the Met Office. They produce one of these charts every 6 hours, and when they do a forecast, they like to forecast about 5 days into the future. And in this forecast, we can see the isobars for different pressure areas. We can see cold fronts and warm fronts, and we can, from this, infer the velocity of the wind as well. And as I said, these are produced every 6 or so hours. And the modern weather forecast is done by using a computer to solve the Navier-Stokes equations. This idea goes back to Louis Fry Richardson, at the beginning of the 20th century, and it was only in the 1960s that computers really became important for solving the Navier-Stokes equations, and our modern weather forecast is derived by solving these equations to predict 5 days into the future. Very similar equations, augmented with other things like understanding of ice and the behaviour of the oceans, are used to predict climate, and they are used to show what will happen to our climate up to about 100 years into the future. As well as solving the equations for the weather, Navier-Stokes equations are also relevant. They help me understand the behaviour of the fluid in my cup of tea here. When you design an aeroplane, you typically do what's called computational fluid dynamics to help understand the behaviour of the air over the wing, and most modern aeroplanes are designed on a computer using fluid dynamic calculations well before you actually build one and fly it. If you want to understand the behaviour of a hurricane and predict whether the hurricane is going to hit you or not, then you solve the Navier-Stokes equations over the large extent of the hurricane. The same equations can be used to look at the weather patterns on distant planets, and Jupiter, for example, has storms, but those storms obey the Navier-Stokes equations. The same equations are used by designers of jet engines to work out how they're going to behave, or of car designers to see how the coolant or petrol or gases flow around the car engine. And I used to work for the electricity generating board, and we used the same equations to work out how power stations will work with all the kind of steam turbines and stuff like that. So Navier-Stokes equations are extremely important, and many industries use them to predict what's going on. However, they are very hard to solve. Even on a supercomputer, they are hard to solve. There are very few exact solutions around, and big computers struggle to find the solutions. One of the reasons for this is that the solutions to them are very complex and can be even chaotic, and we'll talk about that in a minute. Mathematicians are particularly interested in Navier-Stokes equations because at the moment, in 2020, we simply don't know if they have regular solutions at all. What that means is if you start them off with some initial state, we don't know whether that state becomes infinite in a finite time. And in 2020, we don't know, and if anyone could solve this problem, then they would win $1 million from the Clay Foundation. But we're pretty sure that most of the time they do have solutions, and if they didn't, the weather would behave rather differently from the way it does. So, why are they so hard to solve? Well, one of the reasons is shown in this picture of turbulence. Turbulent fluid motion arises very naturally. We see it if you look at a cloud, the very complex motion of the cloud. As far as we know, this incredibly complicated motion you can see in the picture is a solution of the Navier-Stokes equations. So any computer solution has to capture all of this complexity within it. And that is very hard to do. If you look at how complicated that is and all the motion on small length scales, this is very hard to capture. And yet we need to do this in order to be able to predict the behaviour of fluids. Now, one reason for this behaviour, complicated behaviour, is what we now call chaotic motion. In the 1960s, a meteorologist called Edward Lorenz decided to look at a simplification of the Navier-Stokes equations, and what he did was look at convection. And he said, well, there are three principal modes of convection. Let's see how the amplitude of these modes changes with time. So one mode is X, one mode is Y, one mode is Z, and he projected the Navier-Stokes equations onto these modes and came up with what are now called the Lorentz equations. So this was the 1960s, and he had computers available, and so Lorentz put these equations on the computers. And he was then incredibly surprised, because what he found was these three relatively simple looking equations produced incredibly complicated motion. Here is a picture of the motion. This is called a chaotic strange attractor, or sometimes called the Lorentz butterfly, and that is a solution of the Lorentz equations showing the sort of complexity and unpredictability of the motion. And we can now call this chaos, and we recognise that chaos is a vital part of many aspects of the natural world. Lorentz was actually delighted because this unpredictability and complicated behaviour coming out of this simplified system of equations made him realise that a more complicated system than Navier-Stokes could also admit very, very complicated behaviour. And that made him realise that he had an explanation at last for why the weather was so complicated and so unpredictable. And this is basically right. It's why we can't predict the weather more than about 2 weeks in advance. Now, the Lorentz equations are three systems of equations which are ordinary differential equations and which are quadratic in that you have terms multiplied by each other. And a rather similar looking set of equations are currently being used in a very, very important role. And these are the SIR equations for understanding the evolution of an epidemic such as the current COVID-19 epidemic. So just like the Lorentz equations, the SIR equations have three unknowns, S, I and R. S is the number of people in the population likely to become infected. I is the number of people in the population who are infected, and R is the number of people who have recovered from the infection. And there we have the three equations, which superficially look rather like the Lorentz equations. But there is a crucial difference. The Lorentz equations led to motion which was extremely erratic and very, very hard to predict. In contrast, the SIR equations lead to predictable behaviour. And this is very, very important because these equations, augmented with extra complexity, are being used by epidemiologists to predict the evolution of the current COVID-19 epidemic. Let's have a look at them. The solutions. In this picture, we can see the number of susceptible people in the population in yellow, the number of infected in blue, and the number recovered in red. And you can see the number of infected people rises exponentially at the start of the epidemic, then reaches a peak, and then starts to decline. Whereas the number of recovered people slowly increases, and the number of people likely to get the disease slowly decreases. It's the picture of the infected people that's of great importance to us at the moment because it predicts the initial exponential growth that we've all seen, and at the time of the recording of this lecture it looks as though we're just coming out of the peak. And then the equations, the SIR equations, help understand how long the infection is likely to stay. So the Navier-Stokes equations are incredibly important to help us understand the weather and climate, and the SIR equations are very, very important to help us understand the behaviour of epidemics, and they are all examples of nonlinear differential equations. My final equation I call the shower equation, but its official name is the differential delay equation. And in this equation, we say that the rate of change of some quantity x is proportional to what x was at a time tau in the past. And this is a very important equation when we want to control things, because usually when we turn a knob to control something, the effects of doing that are not felt until some time in the future. So I want you to imagine that you are in a shower. We've already had showers once in this lecture. We were singing in the shower. Now I just want you to have a shower. And I want you to imagine that you're in the shower and the shower feels a bit too hot. So you turn the knob to cool it down. But there's a delay in the system. That's due to water going through the pipework, and so the shower actually gets hotter and hotter. And so you turn the knob more and more to make it cold. And after the delay time, the shower suddenly goes cold. And it gets colder and colder because you turn the knob up so much. And you get freezing cold. So what do? You turn the knob up to being hot. Well, nothing happens. The shower continues to get cold. And you wait a bit more, and then suddenly it gets scalding hot. And so you turn the shower down, and you go through a cycle of the shower getting hugely too hot and then hugely too cold. And if you do it wrong, it can go out of control, and you just end up scalding yourself or freezing yourself, and it's a really rotten shower. And that is the problem of controlling something when there is a delay in the system. Well, we can do some analysis of this, and here's a bit of mathematics showing how it's done. The equation that we have is dx by dt is minus lambda times x of t minus tau, and that means that the rate of change of x is proportional through lambda to what x was at some time in the past. And to solve this equation, we make a substitution. We let x of t equals e to the alpha t. We don't know what alpha is at this stage. But if you substitute this into the delay equation and do some mathematics, then alpha ends up satisfying what's called a transcendental equation. Alpha is equal to minus lambda times e to the minus alpha tau. So this is a transcendental equation. It's quite a delicate equation to solve because it involves the exponential function on one side and alpha on the other. Okay, well, what matters in this equation is not so much what alpha is, but how the solution depends upon alpha. And from a mathematical point of view, if alpha is a complex number, which it generally will be, and the real part of it is negative, then the behavior of x is such that it will gradually decay and the shower is controllable. However, if the real part of alpha is positive, then the shower will be uncontrollable. And it turns out that you can work out exactly the value of alpha where this transition between controllability and uncontrollability occurs, and it occurs when lambda times tau is equal to pi over 2. So if lambda times tau equals pi over 2, then that's a transition between controllability and uncontrollability. If lambda times tau is less than pi over 2, the shower is controllable, and if lambda times tau is greater than pi over 2, then the shower is uncontrollable. And we can see that in our picture. On the top, I've done a calculation of the behavior of the shower when lambda tau is less than pi over 2, and you can see that the temperature nicely decays and it's controllable. But if lambda tau is greater than pi over 2, then the shower has these big oscillations that we kind of alluded to in the kind of verbal description, and it rapidly goes out of control. Okay, and this is a common type of problem in anything where you have a delay between what you do and the effects of that delay. So an example of this that occurs naturally in climate is the El Niño Southern Oscillation, which is a sort of fairly irregular warming and cooling of the southern Pacific Ocean, which causes an enormous economic impact. And the reason this satisfies a differential delay equation is that when something happens over in the west coast of South America, that sets up an ocean current which goes all the way over to Asia and then all the way back again. And that introduces a delay because the ocean current takes energy from South America and then brings it back after a time of at least 2 years. So you get a differential delay equation just like the one we had. And with the case of the El Niño, you have actually a fairly chaotic behavior. We looked at chaos in the Lorentz equations, and you get an irregularity. And the irregularity in El Niño is all due to the effects of the delay. Why is this really important? Well, it's really important at the moment because we're trying to control the COVID-19 epidemic by putting in measures, and those measures naturally have a delay in them. If you do social distancing, then it takes time for social distancing to have any effect at all. And we've already seen with the shower that any problem with delay is very, very hard to control. And this means that we have to be very careful as we control the COVID-19 or indeed any other system with delay to make sure that it doesn't go out of control, even though we're trying to do things which we hope will be right. And that's why I've decided to finish these 5 equations with the delay equation. It's an incredibly important equation in technology, and it's an incredibly important equation to us at the moment with the COVID-19 emergency. So I hope you've liked this tour of 5 equations and have seen how they are really, really important in all the sort of technology and all the other aspects of our life. And I would just like to conclude this talk with saying I believe that there's never been a time when an understanding of maths is more important to our lives. Both in the current COVID-19 emergency, where the decisions of the government have to be looked at by scientists and mathematicians to see whether they will have a beneficial impact, but also our understanding of climate change and of the rest of technology. Mathematics is very, very important to all of them. So this has been my last lecture as Gresham Professor of Geometry, and I will say farewell to all of you for that. But it is my very, very great pleasure to hand over to the new Gresham Professor of Geometry, who is Sarah Hart, who is Head of Mathematics and Statistics at Birkbeck College in London. And she's going to be delivering a series of lectures called Maths, Music and Writing. And she will start her series with a lecture on the mathematics of musical composition on the 13th of October 2020 at 1 p.m. in the Museum of London. I must say I'm really looking forward to hearing that lecture myself, and I'm sure that you will too. So bye-bye, and I hope you've enjoyed my Gresham lectures over the last 4 years.
I'm Richard Evans, Provost of Gresham College. It falls to me to thank Chris Budd, not only for today's lecture, but also for all the 24 lectures he's delivered over the past 4 years. He's covered a wide variety of topics, especially on the uses and applications of mathematics in modern life. And they've been engaging, accessible, and attracted considerable audiences, both in person and online. In the past, Gresham professors of geometry used to occupy the chair for quite long periods of time. Benjamin Cowie, 36 years, Samuel Birch for 40 years, Stephen Kittleby for 43 years, and William Wagstaff holds the record for 47 years as Gresham professor of geometry. But in recent times, we've limited the tenure of office to no more than 4 years. So this is the last of Chris's lectures, and we have to say goodbye to him. Been very lucky to have him as our professor of geometry. He's one of Britain's most distinguished mathematicians. He was the top maths undergraduate in his year at Cambridge, which entitled him to be called Senior Wrangler. And then he moved to Oxford to do his doctorate, and he's been applied mathematics professor at the University of Bath since 1995. He's also served as professor of mathematics at the Royal Institution. In 2015, he was made CBE for services to science and maths education. In 2016, he became Professor of Geometry at Gresham College, and he joined a long list of distinguished predecessors since the professorship was established in 1597, including Carl Pearson, Christopher Zeeman, Roger Penrose, most recently Robin Wilson, John Barrow, Raymond Flood. He'll be succeeded by Sarah Hart, who will start this autumn as 33rd Professor of Geometry at Gresham College. More importantly, she is the first woman to occupy the professorship. She's Professor of Mathematics and Head of Department at Birkbeck, the University of London, where she teaches part-time mature students. Like Chris Budd, she is passionate about adult education and reaching out to the general public. She's been actively engaged in the Gresham Society for a number of years and has lectured for us already in 2017. She's got a particular interest in the relationship between the mathematics and the creative arts. And I'm sure you'll all look forward with keen anticipation to her lectures over the next 3 or 4 years. I've heard her speak, and she's indeed very entertaining as well as very informative and thought-provoking. In the meantime, I'm sure you'll all want to join me, if only virtually, in thanking Chris for his lectures over the last 4 years.